Hello everybody, welcome to my Physics 100 class. Today's lecture will be focused on thermodynamics. Last week we talked about the temperature and heat, or we call it thermostatic. Now we talk about the dynamics of heat, or we can call it as a thermodynamics. Learning about thermodynamics will give you the idea how AC or refrigerator work, or even how to cook properly. So if you try to fry the french fries or some vegetables, you need to understand a little bit about thermodynamics to become a good chef. Thermodynamics actually ignites the revolution of Industry 1.0 when engineers used the steam machine for transportation like train and steamboat, and also for the factory machine to produce some goods. And also by thermodynamics, we can understand how do the steam engine and jet engine works. Other example of thermodynamics is the protein or enzyme inside your body. The biomolecules such as protein and enzyme only working properly in a folded state. The increasing temperature can unfold those biomolecules, so they're not functioning properly anymore. The change of this state from folded to unfolded state can be explained using thermodynamics. Other example is the map of the average temperature around the world that will help us in deciding whether the use of solar panel in a particular place is economically feasible or not. So, what is thermodynamics? Thermodynamics is a branch of physics which study about the energy transfer and conversion of heat and work, and also the branch of physics which study about the properties of the system and their interaction with the environment. So, before learning the thermodynamics, we should understand first the system. What is the system? The system is actually the one that you focus on or something that you observe, while the environment is anything outside the system. We have three different kind of system. First, the open system, and then closed system, and the isolated system. For the open system, the mass and energy can be exchanged between system and its environment. So for example, of the open system is ocean. So for example, you're standing on the beach. So there is a free exchange of energy and mass between you and the environment. For a closed system, only energy can be exchanged between system and its environment. For example, in a greenhouse, the heat is exchanged, but no mass is exchanged between the room inside the greenhouse and the open air. For an isolated system, there's no energy and mass exchange between system and its environment. So, for example, the gas molecule inside this liquid petroleum gas chamber is completely isolated from the outside. We can summarize here that we have three different kind of system: the open system, the closed system, and the isolated system. For the open system, like you see from the arrows, the energy and matter can be exchanged, while for the closed system, only energy exchange is allowed, while the exchange of matter is not allowed. For the isolated system, both exchange of energy and matter are not allowed. Now we are talking about the first law of thermodynamics. In the first law of thermodynamics, we discuss the interaction between the system and its environment. So if you see this picture below, if we have a chamber filled with the gas molecule, if you supply some heat to this chamber, basically you supply the energy or the heat, let's call it as a Q, to the system. And what happened to the system, because you hear it, the internal energy of the system will increase. The energetic molecules will push this piston forward, so this gas molecule actually do some works to this piston. The amount of internal energy change of the system is depend on the heat supplied to the system and the work done by the system. We have some convention here. Q is positive when heat is added to the system, and Q is negative when heat is released or emitted by the system. W, work, is positive whenever the work done by the system, while work is negative when the work is done on the system. When we heat the gas inside the chamber, this molecule will push the piston forward. So the work done by this molecule is actually force times the change of position of the piston. And remember that force is equal to pressures times area. And we can write this as work is equal to P times A times delta S. A times delta S, the area, times the change of position, actually tell you the change of volume. So work done by the gas now can be written as pressures times change in volume. So by mapping the state of the gas in a PV diagram like this, we can find the work done by the gas for a particular process from one state, P1 V1, to another state, P2 V2, by looking at the area under the curve. So for example, if you are asked to find the amount of work by the system for this particular process, so you start from this process to that process, so the total work done by the system is the area under the curve. So if you recall from the high school, you've already learned about the Boyle's law, Charles' law, and Avogadro's law. In Boyle's law, actually tell you about the relationship between pressure and volume. And P, pressure, is inversely proportional to the volume. So it means that the bigger the volume, the smaller the pressure. In Charles' law, volume is proportional to the temperature. The higher the temperature, the bigger the volume. And in Avogadro's law, we see the relationship between the volume and the amount of molecules. Volume is proportional to the number of molecules. So the more molecules means the more volume. So P is proportional to T and P proportional to N. So if write them down, so all of those relationships combine, and we can write this: P, pressure, is proportional to the N and proportional to the T, but inversely proportional to V. P equal to NT divided by V. And at this point, we have to add the universal gas constant R, which is 8.314 joule per mole Kelvin. So at the end, we can write like this: P equal to nRT divided by V, or PV equal to nRT. There are some assumptions used in the kinetic theory of gas. First, gases are composed of tiny particles, atoms or molecules, which is small hard spheres, insignificant in volume, and no intermolecular force, either attraction or repulsion. And also, these particles are in a constant random motion, move in a straight line about 1000 miles per hour, and they frequently collide with each other and walls of container. And the collisions between the atoms or molecules are assumed to be perfectly elastic. It means that no energy is lost during that collision. Based on the kinetic theory of gas, we can calculate the internal energy of gas. U is equal to 3/2 nkt, or U is equal to 3/2 nRT. We can use either K, Boltzmann constant, or R, the universal constant of gas. They are connected with the Avogadro number. K, the Boltzmann constant, is actually the universal gas constant divided by Avogadro number, and K is equal to 1.38 times 10 to the minus 23 joule per Kelvin. We can evaluate the basic processes in thermodynamics by using evaluation on the PV diagram. So the first process here is the isobaric process, or constant pressure process. So if the initial condition is this point and the final condition is that point, the initial condition is P and Vi, initial volume, and the final condition is Vf, final volume. If the process is happen at the constant pressure like this, so the work done by the system is the area under the curve. Work is P times delta V, or P the pressure times V final minus V initial. The next process is the isochoric or isovolumic process, or process with the constant volume. So if you see this chamber filled with the gas molecule, if we heat it, you supply some heat or Q, so the change of internal energy of the system delta U is Q minus work. And to show some works, there must be a change in volume. But because this is a process with the constant volume, there is no change of volume, or delta V is equal to 0. When delta V is equal to 0, so W here is 0. So in this kind of process, delta U is equal to Q. The next process is the isothermal process, or process with the constant temperature. Remember that the internal energy of the system is 3/2 nkt. So the change in internal energy of the system is delta U equal to 3/2 nk delta T. Since in this process we have isothermal or constant temperature, so delta T, the change of temperature, is 0. And when the delta T is 0, of course, delta U will become 0 too. And in this case, Q, the heat added to the system, is equal to the work done by the system. And the work done by the system can be explained by this equation: nRT ln V final divided by V initial. So its temperature corresponds to a particular slope of this plot. So if we have a different temperature, we will have a different slope. So suppose if we have a higher temperature than before, so you will have a slope up here. And if we have a lower temperature process, so the slope will be below the slope shown above. The next process is the adiabatic process. In adiabatic process, no heat is exchanged between the system and the environment. So in this case, Q is equal to 0. And if Q is equal to 0, so based on the first law of thermodynamics, delta U will be equal to minus W. Let's take a look at this picture, this plot. So the adiabatic curve is actually the process from one isothermal process to the other isothermal process. In this case, we have two isothermal processes. The first one, this blue line up here with the temperature Ti, initial temperature, and the next is the isothermal process with the temperature Tf, or the final temperature. So this adiabatic process occurred from Ti to Tf. So the work done at this process is equal to 3/2 nR Ti minus Tf. Remember, usually when we talk about the delta T, we talk about the change of temperature from the final to initial, Tf minus Ti, but because now we have delta U equal to minus W, so we change the sequence here, Ti minus Tf. Now we move to the second law of thermodynamics. Naturally or spontaneously, heat is flowing from a higher temperature state to a lower temperature state. Heat can go the other way by applying some works on the system. Natural or spontaneous process tends to disperse or spread the energy. So naturally, change in entropy or delta S bigger than 0. There's one good link to understand the second law of thermodynamics. You can find it here in this YouTube channel. To understand the second law of thermodynamics, we should understand entropy first. Entropy is the degree of disorder of the system. A higher entropy means a higher disorder state of the system. For example, if you see this barbed wire, in the beginning when it first installed, this barbed wire is shiny and clean, but now after some years we see that corrosion in a metal barbed wire. So it means the degree of disorder has increased year by year by year. And natural or spontaneous process prefer to reach the maximum entropy. So according to the second law of thermodynamics, natural process tends to have delta S bigger than 0. One example of the application of the second law of thermodynamics is the Carnot's engine. The cycles of heat engine must be reversible and the entropy must be constant. So this is an idealization. In reality, not all the heat converted into a work. Some of them is dissipated or even wasted due to friction and other reasons. So if you look at this picture, there are 4 processes. First one, the isothermal expansion, and then continued with the adiabatic expansion, and then continue with the isothermal compression and the adiabatic compression. Any system working between two given temperatures, T hot and T cold, can never have an efficiency more than the Carnot engine working between the same reservoir respectively. Also, the efficiency of this type of engine is independent of the nature of the working substance and is only dependent on the temperature of the hot and cold reservoir. One example of the application of the second law of thermodynamics is a heat engine. In a cyclic engine, it is impossible to convert all heat to become work. There's always some heat that dissipated or was wasted during the process. So if you have a hot reservoir with the temperature TH, the heat in a hot reservoir KH will flow to the cold reservoir with the temperature TC. But during this transfer, some of the heat become work here. So the efficiency of the machine will be work divided by QH, or the work done by the engine divided by the heat from the hot reservoir. Using a simple math, we can get a different expression. So the efficiency before is work done by the engine divided by the heat supplied by the hot reservoir. But if you consider the temperature TH for the hot reservoir and TC for the cold reservoir, so we can get another expression like this. The efficiency is 1 over QC divided by QH, or the efficiency 1 minus TC divided by TH. You can just look at this simple math and try to derive this by yourself. We can also have a cooler machine. In a cooler machine, we have a reverse of heat engine. The work is QH minus QC. So we have a hot reservoir TH and the cold reservoir TC. This is not natural, because naturally the heat flow from the hot reservoir to the cold reservoir. But in the cooling machine like this, the heat is flowing from the cold reservoir to the hot reservoir. Why this happen? Because we supply some work. So actually in this process we have more heat here, so that the total heat from here can go to the hot reservoir. So for the cooling machine, we have what we call as a coefficient of performance. Coefficient of performance is defined as QC divided by W.